Have you ever wondered how massive projects like building an aircraft, managing a city's infrastructure, or designing advanced software come together seamlessly? The secret lies in systems engineering, a disciplined approach to solving complex problems by focusing on the big picture. Welcome to my course, The Fundamentals of Systems Engineering. This is Lesson 2. The basics. In the first lesson, we briefly touched on the key principles of systems engineering. Before we dive too deeply into these principles, I would like to first cover some basic terms and concepts in systems engineering. First of all, what is a system? A system is a set of interrelated components working together towards some common objective. What is systems engineering? The key word here being guide. To guide is to show the way. This characterization emphasizes the process of selecting the path for others to follow from among many possible courses, which is a primary function of systems engineering. A dictionary definition of engineering is the application of scientific principles to practical ends, as the design, construction, and operation of efficient and economical structures, equipment, and systems. In this definition, the terms efficient and economical are particular contributions of good systems engineering. Development includes the identification, coordination, and management of diverse fields of expertise in many domain applications. So what do systems engineering and project management have to do with each other? The engineering of a new complex system usually begins with an exploratory stage in which a new system is evolved to meet a recognized need or exploit a technological opportunity. When the decision is made to engineer the new concept into an operational system, the resulting effort is inherently a major enterprise, which typically requires many people with diverse skills to devote years of effort to bring the system from concept to operational use. The magnitude and complexity of the effort to engineer a new system requires a dedicated team to lead and coordinate its execution. Such an enterprise is called a project and is directed by a project manager and aided by staff. Systems engineering is an inherent part of project management, the part that is concerned with guiding the engineering effort itself, setting its objectives, guiding its execution, evaluating its results, and prescribing necessary corrective actions to keep it on course. Recognition of the importance of systems engineering by every participant in a system development project is essential for its effective implementation. To accomplish this, it is often useful to formally assign the leader of the systems engineering team to a recognized position of technical responsibility and authority within the project. Sometimes the leader of the systems engineering team is referred to as the chief engineer of the project. In government circles, systems engineers sometimes double as program managers. In this sense, A program is a collection of projects. Systems engineers transform the needs of the customer into a finished system. They understand what the customer needs and carry the project through from concept development to design, and they play a key role in testing and maintaining the system to ensure it meets the customer's requirements. Systems engineering, therefore, is inherently a highly customer-facing role. Therefore, it is imperative that the systems engineer is well equipped with soft skills. A highly sought after skill of the systems engineer is the ability to translate sometimes highly technical concepts into a language that the customer can understand. The systems engineer must be able to establish and maintain rapport with the customer. Sometimes customers are very technically savvy and sometimes less so. The systems engineer needs to have the ability to read the room and tailor their speech to meet their audience. The systems engineer must be able to fully understand what the customer needs, even if it is sometimes difficult for the customer to communicate those needs clearly, translate those needs into requirements, and ensure that the finished system not only meets the customer's needs, but also creates value for the customer.
The system lifecycle has three stages, or phases. They are the concept development phase, the engineering development phase, and the post-development phase. Technological opportunities and operational deficiencies serve as inputs into the concept development phase, and the outputs are system functional specifications and a defined system concept or concepts. The system functional specifications and a defined system concept or concepts then serve as inputs into the engineering development phase, and the outputs are system production specifications and the production system. These two outputs in turn serve as inputs into the post-development phase. The outputs from the post-development phase are an installed operational system and operations and maintenance documentation.
Now let's look at each phase in further detail. The concept development stage is the initial stage of the formulation and definition of a system concept perceived to best satisfy a valid need. The development stage, as the name implies, embodies the analysis and planning that is necessary to establish the need for a new system. The engineering development stage covers the translation of the system concept into a validated physical system design meeting the operational cost and schedule requirements. The engineering development stage corresponds to the process of engineering the system to perform the functions specified in the system concept in a physical embodiment that can be produced economically and maintained and operated successfully in the operational environment. The post-development stage includes the production, deployment, operation, and support of the system throughout its useful life. The post-development stage consists of activities beyond the system development period, but still requires significant support from systems engineering, especially when unanticipated problems requiring urgent resolution are encountered. Now let's look at a practical example. The following presentation is presented to give you a sense of one of the types of work products that result from the systems engineering process. This particular presentation was created for a design review of the Federal Emergency Disaster Power and Awareness, or FEDPAS system, the Command Center. There are two types of design reviews: the preliminary design review, or PDR, which occurs fairly early in the systems engineering process and gives the customer a chance to see the preliminary design before further engineering efforts are agreed upon. The second design review typically occurs prior to production and is called the critical design review, or CDR. The CDR gives all stakeholders a chance to look at the final design before the system goes into production. So I'm not going to cover each slide or section in detail, and I'll likely skip over some slides quickly so that I can cover just the highlights. So here's the problem context. This is a quick overview of our current problem. Major hurricanes such as Katrina in 2006 and Sandy in 2012 exposed critical gaps in FEMA's disaster response capabilities. These events demonstrated the difficulty of quickly assessing damage, restoring communication, and providing immediate aid to isolated communities. Currently, initial situational awareness often depends on commercial news sources, causing delays in the delivery of essential services. Without reliable communication and power infrastructure, affected populations remain vulnerable and cut off from assistance. FEDPAS overview. The Federal Emergency Disaster Power and Awareness System, or FEDPAS, is designed to close these gaps, ensuring FEMA can rapidly establish situational awareness and communication in hurricane-affected areas. Through advanced sensors, drones, temporary cellular and internet access, and power generation, FEDPAS aims to provide FEMA and partner agencies with real-time data, faster coordination, and immediate outreach to residents. What's the current state of development? Requirements have been defined, objectives, technical specifications, and desired operational capabilities are established. Preliminary feasibility work has been conducted. Early stage evaluations confirm the viability of sensors, drones, power systems, and communication units. Prototype planning has been done. Initial designs and technology demonstrations are underway, focusing on rapid deployment, robust data integration, and cybersecurity. Stakeholder coordination. Discussions with FEMA, the National Guard, Red Cross, and industry partners are guiding interoperability standards and integration protocols. What are the entrance criteria? Before moving into a full-scale prototyping and validation, the following entrance criteria must be met. Validated network capability. We must confirm that communication equipment can handle high data loads and deliver real-time information under disaster conditions. Power and sensor readiness. We must ensure power systems and sensor packages are tested and can maintain continuous operation in harsh environments. Cybersecurity framework. We must establish initial protective measures to secure data and control access. Interoperability agreements. Secure, pre-coordinated communication and data sharing protocols with key emergency response partners. So this is a high-level description of the command center. The command center is the central hub for FEDPAS. facilitating real-time decision-making and operational coordination during post-hurricane response missions. Strategically positioned safely outside the direct path of the disaster site, and is equipped to function continuously before, during, and after the event. In the initial concept, a single central command center as the primary hub for decision-making and operations. Hardened sensors placed before the hurricane to survive and operate immediately after landfall. Mobile Communication Support Vehicles, or MCSVs, communication towers, and surveillance drones deployed post-storm to restore situational awareness and connectivity. And basic data integration and limited interoperability, relying on manual coordination with other agencies. In the final concept, we have a more distributed and resilient architecture. We have enhanced hurricane-resistant capabilities extended beyond sensors to include other system components. We have advanced data integration, improved cybersecurity, the standardized interoperability protocols for seamless coordination with multiple agencies. And we have faster, more efficient deployment and relocation with reduced setup times and automated processes to minimize operator workload. So I won't read through all of this one, but just know that this is the stage in the process where we begin to create tables of specifications and begin to really consider and start to decompose the design. So we can see here that the specifications will need to include operational requirements, functional requirements, performance requirements, external interface requirements, operational requirements, functional requirements, more performance requirements at the physical level, and external interface requirements. As we further dig down into and really decompose those high-level specifications, we need to get into some actual numbers, right? We need to understand what the customer is expecting with in regard to performance of the system, right? So we really begin to dig down deep into the requirements and or create requirements that will meet the customer's needs. So as you're going through and developing the specifications and looking at all the requirements, a lot of times you run into issues. So here is a list of issues that we kind of came up with when we were designing the system, right? There's issues around operational demands for high bandwidth and low latency, where the deployment, the sensors would be deployed. Need to consider operator workload and training. There's going to be cybersecurity challenges. How do you scale interoperability? How do you have adaptability in a complex environment and at scale? These are just some of the things that we need to consider. So here we see the top level functional tree. These are the primary functions of the command center. At the next lower level of the functional tree, we see function 1.1 from the previous slide, further decomposed into lower level functions. And here we see function 1.2, further decomposed into lower level functions. Here are functions 1.3 through 1.5, also decomposed into lower level functions. And here, of course, are functions 1.6 through 1.8, all decomposed into lower level functions. A big part of systems engineering is utilizing modeling tools to create diagrams of the system. This process is called Model-Based Systems Engineering, or MBSE. MBSE is one of the many tools in the systems engineer's toolkit. In this particular diagram, we have an activity diagram, which shows activities which occur within the system and interactions between functions and actors. Another critical part of the systems engineering process is creating n-squared diagrams. Well, that does it for lesson 2. In the next lesson, we'll dig a little further into the process of creating the functional architecture and decomposition work products. After that, we'll move on to the physical architecture of the system. I hope you take the time to visit my websites, and if you're on YouTube, remember to subscribe to my channel if you like the content. Give me a thumbs up on the video if you liked it, and ring the bell so you can get notifications. Thank you for your time. Have a nice day.
Every modern advancement, from electric vehicles to smart cities, relies on systems engineering to bring ideas to life. Systems engineering ensures the world keeps running smoothly. If you would like to further explore the world of systems engineering, or would like more information on how we can work together to solve complex problems and make things work seamlessly, reach out to us at Dollman Systems LLC today.